Good morning, students. Today, let us discuss about the atoms. The very first atom model was proposed by J. Thomson in the year 1898. In the year 1897, Thomson discovers the electron. Thomson discovered the electron from the experiments on the electrical discharges in gases. After the discovery of the negatively charged particle called electron, he concluded that this must be one of the particles from the atoms. Since everybody knows that the atom is an electrically neutral particle or neutral object, since electron has negative charge which is actually coming out of the atoms, there must be some positive charge or equal amount of positive charge in an atom which neutralizes the atom. So Thomson guessed that an atom should have both the positive and the negative charges and proposed the very first atom model known as Thomson's plum pudding atom model. Now Thomson says that every atom consists of a positively charged central core called an atom which is positively charged central globule. In this globule which is positively charged, the negatively charged electrons are embedded here and there. After the proposal of this atom model, there were a few merits. The first merit of the Thomson's atom model is that it explains the charge and neutrality of the atom. The second success is that theoretically this model claims that whenever the energy is radiated from the atom and this energy is in the visible region. This is the second success. This is something very encouraging. But very soon this atom model sought some of the failures. This atom model could not explain the atomic spectrum and a few other experimental phenomena. As a result, this atom model was not a successful one. This was discarded. People could not agree this. Thomson's very own student who was like a research student of the Thomson by name Rutherford took over the study after his discoveries and research work in the field of radioactivity. So Rutherford wanted to propose an atom model. After his constant efforts, Rutherford proposed an experiment called alpha particle scattering experiment, whereby he wanted to propose a new atom model. Rutherford called his own students, two of his students by name Geiger and Marsden, and suggested an experiment to be performed. What Rutherford said is that we should consider a photographic film which is coated with a fluorescent material called zinc sulfide, and a gold film, very thin gold film should be taken at the center of this photographic film, and this gold film should be bombarded by high energy alpha particles taken from a radioactive source such as bismuth. After the suggestion given by the Rutherford, these students have performed the experiment in the year 1906, and the experimental results were given to Rutherford in the year 1910-1911. Thereby Rutherford interpreted the atom model. So what was the exact procedure of the experiment? How did the experiment go on? Now Geiger and Marsden, as suggested by Rutherford, exactly this experiment was carried out like this. They have taken a gold film that was very, very thin. The thickness of this gold film was about just 2.17 into 10 to the power of minus 7 meters. An extremely thin gold film was considered. And we all know this common gold, the most abundant gold, has 197 nucleons in it today, even though people in those days did not know it. And there is about 79 positive charges in the gold nucleus. And they have taken an extremely very, very thin gold film, almost as thin as a tissue paper. Around that gold film, they have taken a photographic film that was coated with zinc sulfide fluorescent material. And the aim was to bombard alpha particles over the gold film. The source of the alpha particles taken was bismuth 214-83, and the alpha particles emitted by bismuth, as it is a radioactive source, was very powerful radiations. The energy of these alpha particles was about 5.5 mega electron volt. This is a highly energetic radiation. Such powerful alpha radiations were bombarded in the gold film. They have observed that most of the alpha particles, that is about more than 99% of the alpha particles, passed undeviated. 99% of the alpha particles passed undeviated without suffering any collisions in the gold atom with the gold atoms. There was only about 0.14% of the alpha particles were scattered. They got deflected or have undergone collisions with the gold atoms and have suffered a deviation about more than 1 degree. The angle of scattering is more than 1 degree, only for a small percentage of the incident alpha particles, that was about 0.14% of the particles. Out of 8,000 particles, just one particle, out of 8,000 particles, just one particle scattered at an angle more than 90 degrees. So the experimental observations we will see once again, there were about 99% of the alpha particles passed undeviated without suffering any scattering or collisions with the gold atoms. Less than a 0.14% or exactly less than 1% of the alpha particles scattered at an angle more than 1 degree. About just one particle out of 8,000 incident particles scattered at an angle more than 90 degrees. These results were given to Rutherford to explain the nature of the atom or otherwise the structure of the gold atom. Rutherford explains about the structure of the gold atom based on these experimental inferences. If 99% of the particles have to pass through without any deflection, without suffering any collisions, then there must be large amount of empty space in a gold atom. Without so much of empty space, so many particles cannot pass simply through the gold atom. Secondly, if there was a small percentage of the particles which got deflected by an angle just more than 1 degree, these particles should have suffered some deflection or some reflection from the positive charge present in the gold atoms, which means the gold atom has the positive charge, and this positive charge is not distributed all over the gold atom but should be confined to a very, very small space. And about one particle of 8,000 incident particles got deflected at an angle more than 90 degrees. And there were also particles which were deflected at an angle of 180 degrees, and they were coming back, bouncing back in the opposite direction. This made Rutherford come to a conclusion that every atom consists of a positively charged central core called a nucleus, and this nucleus, this positive charge, is confined to an extremely small space, and the rest of the space in the atom is empty. There is a large amount of empty space. Comparatively, if the nucleus occupies just 1 unit of the empty space, rest of the space, that is nearly about 10,000 units of empty space, is occupied by nothing. Or otherwise, the atom has large amount of empty space, and in that empty space a small space is occupied by the nucleus which is positively charged. Now the question comes, where are these electrons which were supposed to be the members of the atomic family? These electrons are simply distributed in various places but revolving around the nucleus. So Rutherford now is proposing a planetary atom model. So these electrons are revolving around the nucleus in some stable orbits. This is what Rutherford says. So therefore, according to Rutherford's atom model, there is a nucleus. Around this nucleus, electrons are revolving in stable orbits. This is what Rutherford said. From Rutherford's atom model, we can even derive the expression for the radius, velocity and energy as well. But very prominently, we should see the merits and demerits of the Rutherford's atom model. According to this atom model, Rutherford is able to calculate the radius of the nucleus, or otherwise the size of the nucleus. The size of the nucleus as predicted by Rutherford is about 10 to the power of minus 15 to 10 to the power of minus 14 meters. These are radius of the nucleus. Now another question comes that when the alpha particles are passing through the gold atoms, why were these alpha particles not influenced by the negatively charged electrons present in the atom? These negatively charged electrons are very, very light compared to the alpha particles, therefore they were not influenced by the electrons and they simply passed undeviated or whatever that we have discussed earlier. So this way, Rutherford proposed the planetary atom model. This model has sought some of the merits as well as demerits. What are the merits? This model is a stepping stone to the successful atom model, which was later proposed by Niels Bohr and other scientists who developed the atom models. The first success is that Rutherford discovered the presence of the nucleus. Secondly, Rutherford said that the electrons revolve around the nucleus in stable, or otherwise, shall I say, in equilibrium orbits. No idea what kind of orbits they are there, the electrons are stable around the nucleus. This is what Rutherford said. But there were also demerits. What are the demerits? Demerit number one is this: if electrons revolve around if the electron revolve around the nucleus in a given stable orbit, continuously this electron has got some centripetal acceleration towards the nucleus. If there is centripetal acceleration due to the centripetal force, this electron has to continuously lose the energy. If the electron loses the energy, it cannot stay at exactly the same distance, a given distance from the nucleus. As a result, this distance, or otherwise the radius, decreases continuously. If the radius decreases continuously, the speed of the electron should increase as per the classical physics. As the speed increase, that is the angular velocity increase, the electron eventually has to spiral down, emitting greater and greater and greater amount of energy, finally should fall into the nucleus. As per this theory, the electron should collapse into the nucleus. Before it collapses into the nucleus, it should have emitted continuous radiation of higher and higher and higher energy, or otherwise smaller and smaller and smaller wavelengths. But practically this was not observed, but most of the experiments have revealed that any atom should be able to emit some discrete wavelengths only, a few particular wavelengths only, which were the fingerprints of those particular atoms. So the theory says that all possible radiation should be emitted, whereas experiments say there are only few radiations possible. Hence this atom model has seen a biggest failure. And this atom model also is therefore not explaining the stability of the atom. There were few other failures. Due to these failures, the Rutherford's atom model was not considered, was not accepted completely. Even though there are few merits, the model was not accepted in those days. The model was in fact proposed in the year 1911. The very same year, in the month of January, this atom model was proposed. In the month of December, this was not completely accepted by the scientist community. As a result, to overcome these failures, another scientist, his successor, Niels Bohr, comes into the picture. Before that, we will once again see the few definitions from the Rutherford's atom model. There is something called impact parameter. What is impact parameter? We can now consider this to be the gold atom or gold nucleus. Now these are the incident alpha particles. When the alpha particles are incident on the gold film, some of the alpha particles went undeviated. These are the ones which are traveling far away from the gold nucleus, which went undeviated. These particles did not undergo any collisions. Those particles which came very close to the gold nucleus suffered scattering, otherwise they suffered collisions. In a simple way, they suffered collisions and got deviated at these angles. Now if the perpendicular distance between the initial velocity vector and the center of the gold nucleus, that is this distance, the perpendicular distance between the incident velocity vector and the center of the gold nucleus, this distance is called the impact parameter. Greater the impact parameter, smaller the impact, otherwise they don't suffer much of the scattering. Smaller the impact parameter, they will be at a greater impact and suffer a greater angle of scattering. So what is impact parameter? Therefore, it is the perpendicular distance between the incident velocity vector. For example, if this alpha particle ray we consider, this is the initial velocity vector's direction. The perpendicular distance between the initial velocity vector and the center of the gold nucleus is the impact parameter. The another definition that we need to know is the distance of closest approach. What do you mean by distance of closest approach? Now when you consider a particle which straight travel towards the gold nucleus and undergo a head-on collision, when it is about to undergo a head-on collision, this particle will have certain kinetic energy. This incident particle which is traveling straight onto gold nucleus to the center of the gold nucleus has some certain kinetic energy. Since there is a repulsion between the alpha particle, an alpha particle has 2 units of positive charge, whereas the gold nucleus has 79 protons, that is 79 positive charges. Therefore, the alpha particle with two positive charges experience a strong repulsion from the gold nucleus, which has 79 positive charges. As a result, the kinetic energy slowly drops and then gets converted into potential energy. At a closest point, the entire kinetic energy gets converted into potential energy for this alpha particle. The distance at which this happens is called the distance of closest approach. Therefore, how do we define distance of closest approach? It is that smallest distance of the alpha particle from the gold nucleus at which the total kinetic energy is converted into the electrostatic potential energy. Okay, so with this, now we complete with the Rutherford's atom model. Now we can move on to the Bohr's postulates, the Bohr's atom model. Now Bohr went to the Rutherford's laboratory for about nearly 2 years. Bohr studied Rutherford's lab and he wanted to make certain changes and he wanted to incorporate a few of his quantum ideas into the atom model and make the atom model a successful one. After Bohr's investigation of the Rutherford's laboratory, he came to these following new changes into the atom model. Bohr proposed 3 important postulates. Postulate number 1. Bohr was in total agreement with what Rutherford said, in fact. In his first postulate, Bohr says that the electrons revolve around the nucleus. Electrons revolve around the nucleus in certain stable or allowed or permitted orbits called stationary orbits. He is introducing an orbit called stationary orbit. Any electron that revolves in a stationary orbit does not lose the energy. The energy of the electron remains constant in a stationary orbit. Unlike what Rutherford said, unlike what Rutherford's atom model suggested, that the electron loses energy continuously. Whereas here, the electron possesses a constant energy, it does not lose the energy. Therefore, the distance between the electron and the nucleus, that is this radius vector of the orbit, will always remain a constant. In the sense, in any stationary orbit, energy remains constant. The radius of the orbit also remains constant. And the electron is not losing any part of the energy. So this is what called stationary orbit. Postulate number 2. Second postulate, often called as a puzzling postulate proposed by Niels Bohr. What is the second postulate? Bohr says that an electron which revolves around the nucleus in a stationary orbit possesses an angular momentum that is equals to integral multiples of the h by 2 pi. The angular momentum of an electron which revolves around the nucleus in a stationary orbit is equals to the integral multiples of the h by 2 pi, where h is called the Planck's constant. Planck's constant has a value of 6.625 into 10 to the power of minus 34 joules into seconds. Joules into seconds. This is the Planck's constant. So this postulate is often called the puzzling postulate of the Bohr. We will see the reasons a little later in this chapter. At the same time, classically we know the angular momentum is a cross product of the radius vector and the linear momentum vector. Anyway, when the electron revolves around the nucleus, the linear velocity vector is perpendicular to the radius. So the angle between these two is about 90 degrees. Considering this rp sin theta, it will become rp, which is nothing but mv, which is momentum, into the r. So hence therefore the angular momentum classically is mvr. So hence this expression can also be taken as mvr is equals to nh by 2 pi. We will use this expression a little later. Moving to the third postulate, the Bohr says that whenever the electron jumps from a higher energy orbit to a lower energy orbit, say for example, you have 2 orbits here, 2 stationary orbits, an orbit with energy En2. If an electron jumps from a higher energy orbit to the lower energy orbit, only then it loses the photon. If an electron is just there in one stationary orbit, as long as it is present in one stationary orbit, it does not lose the energy. but only when the electron jumps from a higher energy orbit to lower energy orbit, then this electron loses its energy in the form of an electromagnetic wave, or otherwise called a photon. How much of energy will be liberated in this case? The electron loses an energy that is equals to energy difference between the two orbits. That is, the difference in energy is En2 minus En1 is equals to h nu, that is the energy of a photon, is liberated. So, let me mention this point once again. Whenever an electron jumps from a higher energy orbit to a lower energy orbit, the electron loses an energy that is equals to energy difference between the two orbits. That is, delta E is equals to energy of the higher orbit minus energy of the lower orbit is equals to energy of a photon. Though it is an electromagnetic wave, today we know that this electromagnetic wave is nothing but a photon. This is nothing but the energy of a photon. So these three postulates were proposed by Bohr. There was one important point Bohr even considered from the Rutherford's atom model. In the Rutherford's atom model, it was said that the electrostatic force of attraction between the electron and the nucleus provides the necessary centripetal force. So therefore, the centripetal force as per Rutherford is equals to the electrostatic force. This particular idea is also considered by Niels Bohr without any change. So most of the ideas proposed by Rutherford were accepted by even Bohr. So as per this, even Bohr says that the centripetal force mv square by r is equals to the electrostatic force between the nucleus and the electron. Is charge on the nucleus is Ze. Ze, because Z is the number of protons, E is the charge on each proton. The total charge on the nucleus is therefore Ze, and the charge on the electron is E divided by the square of the distance between the nucleus and the electron. So even though the above three postulates are proposed by Bohr on his own, he also even considered one idea given by Rutherford. So with these ideas, now Bohr successfully explains the atom model. Now after the introduction of the stationary orbits, the atom has gained stability. Unlike Rutherford's atom model couldn't explain the stability, Bohr's atom model explained the stability. This was the greatest failure in the Rutherford's atom model that was overcome by introducing the stationary orbits. Further, based on these postulates, we can derive an expression for radius, velocity and total energy, even the frequency emitted whenever there is a quantum transition, whenever there is a jump. Or otherwise, we can even derive an expression for the wavelength emitted. Nu is equals to c by lambda, therefore h nu can be written as hc by lambda. We can derive even an expression for the wavelength emitted, the wavelength of the photon emitted during this transition. Now let us see those expressions. Expressions for radius of the stationary orbit, velocity of an electron in the stationary orbit, kinetic energy of the electron, potential energy of the system, total energy, wavelength emitted. So now the expression for radius of an nth stationary orbit, of an nth stationary orbit. To derive an expression for radius of an nth stationary orbit, let us once again consider a particular atom, can be hydrogen or any atom. In fact, Bohr proposed this entire theory only for the hydrogen atom. Right now, let us consider any atom with Z number of protons in it and an electron revolving around the nucleus. Let the linear velocity be directed along the tangent. The distance between the orbit and the nucleus is its radius. We need an expression for it. For which, let us now depend on the Bohr's postulates. Let us consider the angular momentum quantization condition. The second postulate is called angular momentum quantization condition, and the expression given by Rutherford, that is centripetal force is equals to electrostatic force. From the angular momentum quantization condition, that is L is equals to mv/r is equals to nh divided by 2 pi. Let's call this as equation number 1. Let's also consider to postulate or otherwise the important suggestion given by Rutherford, mv square by r is equals to 1 by 4 pi epsilon naught ze square divided by r square. Call this as equation number 2. In equation number 2, let us simplify this expression only for mv square. So we can cancel 1 r the both sides. Hence we will be getting an expression for mv square. Expression for mv square is 1 by 4 pi epsilon naught ze square divided by r. Call this equation number 3. Now we needed an expression for the radius, but we don't want the term velocity in either of the expressions. Therefore, let us substitute for velocity here from the equation number 1. In the sense, from equation number 1, we can write expression for v. What is v from equation 1? V is 1 by mr into nh divided by 2 pi. You can observe, I have moved the term m and r to the other side of the equation. So we got v. Therefore, we can substitute here. In equation 3, we can substitute. So we will substitute for v in equation 3. As you substitute, what do you get now? M into 1 by square of the v, m square r square, n square h square divided by 4 pi square that you get after substitution for the v square. The other side of the equation remains as it is, 1 by 4 pi epsilon naught ze square divided by r. Both the sides, 1 pi can be cancelled both the sides, and m can be cancelled both the sides, and r can also be cancelled. Now rearranging the terms, we needed an r. We'll move this to the other side of the equation, rearrange the terms. Then you get r is equals to, moving this epsilon naught to the numerator of the other side, we get epsilon naught. Cross multiplied epsilon naught here, epsilon naught n square h square divided by, I have a pi here and m here, pi m, ze, when we shifted this to the other side, comes to the denominator ze square. So I've got r is equals to epsilon naught n square h square divided by pi m into ze square. This is the expression for radius of nth stationary orbit, any stationary orbit in a particular atom, an atom with atomic number z. Now, if you want to apply this only for the hydrogen atom, since Bohr applied all his theory to only hydrogen initially, for hydrogen, we know hydrogen has got just one proton as its nucleus, hence the atomic number is just 1. Then Rn is epsilon naught n square h square divided by pi m into e square. So this is the radius of stationary orbit in a hydrogen atom. You observe this equation, we have a lot of constants here. Epsilon naught is a constant, that is absolute permittivity. H is Planck's constant, m is a mass of the electron, is a constant, E is a charge of the electron, that is also a constant. Knowing all these constants and substituting them, we get that 0.53 10 to the power of minus 10 meters. The only thing that we have not substituted for is the n, that is n square. So this is the radius of an nth stationary orbit in a hydrogen atom. Observe now, the radius is directly proportional to the square of the orbit number, otherwise called the principal quantum number. As the principal quantum number increase, as a square of the principal quantum number increase, the radius also increases. If it were to be, say, for first orbit of hydrogen atom, for n is equals to 1, n is equals to 1 is called Bohr's orbit. If n is equals to 1 and z is also 1, we call that orbit as Bohr's orbit. For Bohr's orbit, therefore, R1 is equals to 0.53 10 to the power of minus 10 meters. Minus 10 meters is an angstrom. So, in a simple way, we can write the first orbit's radius to be 0.53 angstrom. That's how, in an easy way, we can derive the expression for radius. based on the same postulates, we can also derive an expression for the velocity of the stationary orbit. From the same postulates, we can derive the expression for velocity. We know the velocity of the electron which is revolving in circular stationary orbits is directed along the tangent to the orbit. So whose expression we need to get now, right now. So once again depend on the same postulates even to derive expression for velocity. So expression for velocity of an electron in an nth stationary orbit. Let me not redraw the figure once again, which we have it already with us. Let us consider the same two equations, equation 1 and equation 2 once again. We know from the angular momentum quantization condition, we have mvr is equals to nh by 2 pi, say equation 1. From equation 2 we know mv square by r is equals to 1 by 4 pi epsilon naught ze square divided by r square is equation 2. Again we can cancel one r on both sides, we have got for mv square. Since we wanted expression for velocity, let us not have the radius term here. In the sense we have to cancel the radius from the expression. So what we do is, let us divide equation 2 by 1. When you divide equation 2 by 1, left hand sides mv square divided by mvr. Right hand sides I have a ze square divided by 4 pi epsilon naught r in equation 2. Multiply this by the reciprocal of the first equation, that is 2 pi divided by nh. Cancel whatever terms possible. One mm can be cancelled, a v and a v can be cancelled, an r and an r can be cancelled. Now rearrange the terms once again. 2 pi goes for 2 times. So therefore v, velocity in the nth orbit, v is equals to, we get ze square divided by 2 epsilon naught nh. This is the expression for velocity of an electron in an nth stationary orbit in a given atom, in an atom with atomic number z. So if you once again substitute for the charge on the electron, the absolute permittivity and the Planck's constant. So permittivity, Planck's constant, charge on the electron, let us substitute. When you substitute, you get Vn is equals to 2.18 into 10 to the power of 6 meters per second is a velocity into z by n. So as the atomic number increase in a particular given orbit, the velocity should increase. Or for a given atom, that is when z is constant, as the orbit number increases, as a principal quantum number increase, the velocity decreases. Radius was directly proportional to the orbit number, whereas velocity is inversely proportional to the orbit number. Therefore, as the orbit number increase, the electrons slow down. In the sense, if this is a nucleus here, an electron very close to the nucleus with n value small, say n is equals to 1, there is a particular amount of velocity 2.18 10 to the power of 6 meters per second. If it is second orbit, then this velocity should be divided by 2. The velocity decreases 2 times. Velocity reduces by half. Similarly, if it goes to the third orbit, given fundamental velocity divided by 3 and so on, the electron slows down as it goes away from the nucleus. Further, if we consider for hydrogen atom, only for hydrogen atom, we know the atomic number is z. So the velocity Vn is 2.18 10 to the power of 6 meters per second divided by n. And for Bohr's orbit, we know what is Bohr's orbit now. Very first orbit of hydrogen atom is the Bohr's orbit. That is when Z is equals to 1 and N is equals to also 1. The orbit is called Bohr's orbit. So for Bohr's orbit, that is N is equals to 1, the velocity V1 is equals to 2.18 into 10 to the power of 6 meters per second. So this is the expression for velocity and for the hydrogen atom and for the Bohr's orbit. Similarly, the way we derived expression for radius and velocity, we can also derive expressions for the total energy of the electron in a hydrogen atom. So, expression for total energy. Expression for total energy of an electron in a stationary orbit. We know the electron is in continuous motion around the nucleus. Since the electron is in motion, it possesses its own kinetic energy. Let's say here is the electron right now, whose linear velocity is directed along the tangent. Since it is moving, it has kinetic energy. And this system is a bound system of an electron, negatively charged particle, and a nucleus which is positively charged particle. So we have a bound system here. In the system we have a negatively charged particle called electron and a nucleus which is positively charged. Nucleus has plus Ze amount of charge and the electron has minus E amount of the charge. Therefore, the system also possesses some potential energy. So therefore, there are two energies for this particle, for the system. One is kinetic energy, the other one is potential energy. Therefore, the sum of these two energies is the total energy of the electron. Hence, to get the total energy, we need to add the kinetic energy and the potential energy. So how do we get the expression for the kinetic energy? Let us get the expression for kinetic energy first. Kinetic energy. Once again, from the Bohr's postulates, one of the postulates that we have already taken, that is equation number 2 of our previous derivation. Now we know from the equation mv square divided by r is equals to 1 by 4 pi epsilon naught ze square divided by r square. From this equation, we can get expression for mv square. Mv square is therefore ze square divided by 4 pi epsilon naught into r. Therefore, you know what is kinetic energy? Kinetic energy K is half mv square. If it is half mv square, the K then becomes half times mv square. We can substitute from the previous expression. It is therefore 1 by 4 pi epsilon naught, nothing but this equation, into ze square divided by r. This is your kinetic energy without the radius substituted in the expression. Similarly, we can also get the expression for potential energy. Potential energy U, kinetic energy K, potential energy U. What is potential energy? Potential energy for this bound system, a system of a negative and a positive charge, is minus 1 by 4 pi epsilon naught, charge on the nucleus, charge on the electron. In fact, this negative sign belongs to the charge on the electron in this expression, divided by the distance between the two particles. So these are potential energy. We can add these two in order to get the total energy. Therefore, the total energy can be obtained by adding these two terms. Let's say, therefore, the total energy is a sum of these two. We observe that what is there inside the brackets of these two terms are the same. they don't differ. So we can take this term in the brackets as common. So hence we get 1 by 4 pi epsilon naught ZE square divided by R, which is common. And in the first term we have a half, in the second term we have a minus 1. So half minus 1. So hence the energy becomes minus half of 1 by 4 pi epsilon naught ZE square divided by R. Without the radius being substituted, this is the expression for an electron. Now we know, as the radius change, energy also changes. Hence let us substitute for radius and get the final expression for the energy. You know what is the expression for radius? We have already derived this. R is equals to epsilon naught n square h square divided by pi m into ZE square. Putting it back in the previous expression, then we get E is equals to minus 8 pi epsilon naught multiplying 2 inside ZE square divided by radius term is epsilon naught n square h square divided by pi m into ZE square. Let's check what are the terms that we can cancel. A pi here can be cancelled. None of the other terms can be cancelled. So let us rearrange the terms. When you rearrange this, the energy of the electron in the nth orbit, see m goes to numerator, z goes to numerator and becomes z square here. E square goes to numerator, becomes e power 4 here. Hence minus, the numerator is minus m, z square e power 4, the whole divided by 8 into, we have a epsilon naught into epsilon naught square, n square h square, minus m z square e power 4 divided by 8 epsilon naught square n square h square is the final expression for energy of an electron in an nth stationary orbit in a given atom. Right now, since we always applied for hydrogen atom as was proposed by Niels Bohr, if it is for a hydrogen atom, of course we take Z to be 1. Even before we do that, let us once again substitute the values of these constants: mass of the electron, charge of the electron, absolute permittivity, the Planck's constant. Just retaining Z and N and substituting for the remaining constants and expressing the energy in terms of electron volt. If we directly substitute the values of these and simplify, we would be getting the expression, the value in terms of joules. Later we will convert that into electron volt and finally expressing the value, we will be getting minus 13.6 electron volt as the energy into Z square divided by N square. Further, for only hydrogen atom, for hydrogen, if you substitute Z is equals to 1, then the energy becomes E n is equals to minus 13.6 electron volt divided by N square. Again for Bohr's orbit, we know again what is Bohr's orbit. The very first orbit of the hydrogen atom is called the Bohr's orbit. For Bohr's orbit, you know, n becomes again 1. Therefore, the energy in the very first orbit E1 is minus 13.6 electron volt. So this is how we have derived almost all possible required expressions: radius of the orbit, stationary orbit, velocity of the stationary orbit, and even the total energy of an electron in the stationary orbit. We have one more last derivation in this chapter to complete, that is the expression for the wavelength of an electron, wavelength of the radiation emitted when an electron jumps from higher energy orbit to lower energy orbit. We'll just do that last derivation to complete this chapter.